are in listen-only mode.
Hello everyone, welcome to our webinar on quantifying the effects of discharge on groundwater exchange and temperature in rivers. My name is Paul Gannett and I'm Product Marketing Manager here at Onset for our environmental products. I'm going to give you a brief introduction and then I am going to turn over the presentation to our real expert on the subject. We will have time for questions at the end, but if you have questions as we go, feel free to type those in to the GoToWebinar control panel. We will try to answer some of these questions as we go. For those that we don't get to during the presentation, we will address those at the end or follow up by email if needed. We are recording this webinar, and we will send you a link to the recording afterwards so you can refer back to it in the future. Sorry about that pause. First, a little bit about Onset, for those of you who don't know us. We are the company that makes the HOBO and Tidbit data loggers, which are used around the world for a wide range of applications. We've been making data loggers since 1981, and we've sold over 2 million of them. We have 120 employees here on Cape Cod, Massachusetts, which is where we design and assemble all of our products. Now I would like to introduce our presenter. We are very happy to have with us hydrologist and river systems scientist Erin Bray. Erin is a PhD candidate with the Bren School of Environmental Science and Management at UC Santa Barbara. She has extensive experience in hydrology research, modeling, and environmental planning. Erin will be talking about her research in the San Joaquin River, including what she learned about the river and groundwater dynamics, as well as her methods for deploying data loggers and analyzing the data. So here's Erin. You can take it away, Erin.
Thank you, Paul. Thank you, Paul, and hello, everyone. Thanks for joining us today. So, as Paul mentioned, none of you we won't be able to hear you speaking during the webinar. So, feel free to submit any questions, and if I don't get to your question throughout or at the end, I'll be sure to respond by email over the next couple of weeks. So, just to get started, today I'm going to discuss a few field methods to measure stream temperature and pore water temperature in large rivers and also in the shallow hyporheic zone beneath large riverbeds. My research investigates the patterns and controls of groundwater surface water exchange, and it's studied in a managed lowland river by the use of stream bed and subsurface temperature monitoring using HOBO temperature sensors, and I also use other observations and other field techniques which won't be included in the talk today. By measuring temperature in rivers, it's possible to elucidate the main mechanisms that control different physical processes. The use of heat as a tracer in hydrologic systems has a long history, and you can track thermal pulses or estimate fluid fluxes, and the importance of that has to do with salmon habitat in this particular study. My interest is to quantify the effect that changes in river discharge have upon temperature, but also on groundwater surface exchange. I'll focus today on measuring temperature at the meander bend scale rather than the whole river scale to better understand the processes of groundwater exchange through channel bed forms, or as some people call them, gravel riffles or riffle pool sequences. In this presentation, I'll focus primarily on deployment and retrieval techniques in large rivers and then present 3 distinct applications of using HOBO temperature loggers in large river environment. So here's a slide showing the experimental setting. It's my research is in a large regulated 260-kilometer reach of the San Joaquin River located in the Central Valley of California. The study reach is located along a stretch of river beginning immediately downstream of Friant Dam, which is where the flow releases are operated, and it extends to the confluence with the Merced River. This 260-kilometer reach is currently the subject of an ongoing large-scale flow experiment that began in October of 2009. What we're interested in is the timing, the magnitude, and the duration of those flow releases from Bryant Dam during this 2-year period and use that as a unique experimental opportunity during which we investigate the differences in stream temperature and also potentially differences in groundwater surface exchange. Here's a closer view of the study area. As you can see, the focus of our map is showing the 240-kilometer reach. The map highlights the location of Reach 1, where I focus the smaller scale analysis and also talk about for the rest of this webinar. The colors are showing the changes in different meteorological stations that are used to also conduct heat balance analyses later down the road. There's a significant diversion on this river called Chowchilla Bypass that's just downstream of Reach 1. And then also all of the dots are showing the dense monitoring network that's in place already. So there are 150 locations of stream temperature wells or loggers that have been in place since 2004. And most of these are operated by different agencies, and only some of them are mine. So what this slide is showing is kind of why we're interested in measuring stream temperature and what it can be used for. So the motivation for a meander bend scale field investigation is based on what's shown in these plots. So this is a graph showing the 2-year experimental flow hydrograph at 2 different points in the river. So the top graph, River Mile 267, is located immediately downstream of Bryant Dam, where the flow releases are taking place. And River Mile 229, shown by the bottom graph, is the hydrograph 60 kilometers downstream, and there is, in general, mostly a losing reach. Overlaid on stream flow is stream temperature in dark red, the diurnal variation of stream temperature in orange, and air temperature is shown with the blue line. So as you can see, water that enters upstream, the top graph, is somewhere between 10 to 14 degrees Celsius. But within 60 kilometers downstream, stream temperatures increase to as much as 30 degrees Celsius. Emerging from the lower figure, we recognize that stream temperatures converge upon air temperatures during the summer months. So we want to know what are the dominant physical mechanisms that govern stream temperatures in large rivers where pathways of flow and heat are disturbed by hydrologic alteration at a dam. And my main interest is looking at the field and modeling aspects at the pool riffle scale or at the meander bend scale. So the interest in the pool riffle scale shown here arises from potential perturbations to flow and heat due to hyperrheic flow at short length scales in the gravel bedded reach, which is what I showed earlier, that Reach 1 area. Local variations in near bed temperatures may respond differently under different flow releases, and we're not sure exactly how. This is particularly important for salmon spawning, incubation in the gravel, and emergence of the salmon once they are born. At the meander bend scale, I conducted 3 different field experiments across the length of pool riffle sequences in the water surface as well as in the gravel bed. So this diagram is showing those 3 different field experiments, one involving a fiber optic cable, one involving the installation and digging of artificial redds into the subsurface, into the gravel, and then one showing one study of Riffle pool sensors, so locating sensors in the water column, but with a specific array design in mind. So now I'm going to discuss some field methods of deployment and retrieval of the temperature loggers, and then discuss their application across those 3 different types of field experiments, but I'll focus mostly on the experiment involving placing temperature loggers in the water column in a large river. So as many of you have probably experienced, conducting a successful deployment of any monitoring equipment can be very challenging. And working in large rivers, it's very unlike small streams. Large rivers present complications such as high flows, deep water, swift currents, turbulence, and also the ability to transport sediment and large woody debris. Also, you can't place sensors on the stream bed in a large river if you're not wearing a wetsuit, because typically the water is too deep and wearing river waders just won't cut it. So when you're planning your own monitoring program, it would be really good if you thought through how to deploy the loggers so that they aren't lost. Shown here are some of the items that I use to deploy HOBO ProTemp V2 temperature loggers for a wide range of flow events and for a fairly long deployment. There are anchors, cable ties, pit tags, the loggers themselves, and a solar shield for the loggers. The loggers fit tightly inside the solar shield once they're launched. Then I slide a very small pit tag inside the white sleeve of the solar shield. So those pit tags are just those very small items, bottom center of the screen next to the logger. And they fit snugly inside those white shields, and that tended to work pretty well. I then use stainless steel cable ties through the loop of the HOBO logger once it's inside the shield and connected it to the anchor. And in this case, the anchor that I used was a very large, very heavy concrete paver. I used a number of these. The concrete pavers worked well because they're flat, they don't protrude up off of the bed, and so they don't have a lot of roughness to pick up into the drift to cause any sort of additional turbulence in the water column. So when planning your deployment of sensors, your primary concern will be to moor the sensors in a manner that they won't be swept out of the river. You want to be able to retrieve them. So in some locations, you might also be concerned that your sensors could be stolen or moved by people who are using the river recreationally. So your secondary concern will be to camouflage them. Shown is a photo of those deployment techniques that I found successful and unsuccessful. So on the left, what we see is a photo before deploying a logger using a concrete paver as an anchor in the riverbed. And in this study, in the pool Riffle study, I was interested in measuring water temperature at the sediment-water interface. And so I wanted the loggers to be very tightly secured to the bed. On the right are two photos attempting to deploy loggers by tethering them or tying them to natural structures in or adjacent to the stream. For long-term deployments or for large river deployments, the tethering strategies I found to be unsuccessful. The pros of anchoring the sensors as opposed to tethering them is that they can sustain flows, fairly high flows, and not move. So that particular paver shown in the photo sustained flows of 7,000 CFS and didn't move. It stayed there for almost 12 months. If you anchor your sensors and there is debris and tree branches that are mobilized during high flows, they won't snag if they're properly anchored, but if you have tethered your sensors, it's possible that they'll snag and just be carried away. The other pro of anchoring your sensors in this way is that you don't alter the natural bed material. So if you are considering different permitting issues and disturbance of the bed, pounding rebar into the gravel may not be necessary. Some of the problems with anchoring sensors that you should be aware of is that sediment deposition could significantly bury your sensors and your anchors if you leave them in stream for a long time. And chances are you'll go back out to find your sensors. It'll seem like they've disappeared, but in some of our cases, they were actually just completely inundated with sand and we had to dig them out. You should also remember that if you're going to anchor your sensors this way, retrieving them requires at least 2 people to go out and get them and underwater snorkeling. The other problem with anchoring sensors is that sometimes it can be difficult to relocate them or see them underwater when you're doing this in a large river. So in our case, when we went out to find them, if your pit tag antenna doesn't work correctly or only works in very close range, or say your GPS device runs out of battery when you're in the field, you need to have, you'll need to have a snorkel mask and really look around to find them. But luckily these pavers, because they're square and sometimes brighter than the river rock in color, they can stand out. They do appear pretty different when looking for them. So to answer the questions at the meander bend scale, I'll briefly describe the field investigation for the 3 different studies that I did. The first field experiment I completed last year involves long-term deployment of HOBO Pro V2 temperature loggers, and they were deployed in separate arrays of 3 loggers each. So the Riffle pool near-bed temperature study addresses near-bed temperature monitoring and how temperatures compare spatially and under different conditions of flow. As shown in the map, I installed 4 arrays of temperature loggers in potential zones where there may be some downwelling or upwelling of hyperreic exchange within reach 1, so where those Riffle pool sequences are. They measured temperature at 4 locations in an array of 3 loggers. So one was placed at the head of the Riffle, one was placed at the tail of Riffle, and one was placed at the bottom of the pool immediately downstream of the Riffle. The Riffle pool study aimed to detect changes in hyperreic temperatures. So even though we were measuring temperature in the turbulent flow of the water column, so the sensors were located in the bed, we positioned them as closely and kind of wiggled them down into the gravel as much as possible to pick up any difference in signal that we could find at the riffles. So what this map is showing, the center line is the main channel in the blue. The black and green pools on the side of the channel that you can see in the aerial photo are actually gravel mine pits. And my arrays of Riffle pool temperature loggers are shown in yellow triangles, and operational flow gauges are shown in light blue. So methods of retrieval. I'm guessing a lot of you have used these loggers before, and in a lot of cases you can, find that your loggers have moved or you can't find them at all, and retrieving loggers can be quite challenging. So part of the problem is that when you go out in a large river, you can't wear waders. They'll fill up with water if you're bending down or if you're putting on a snorkel mask to look around, say your GPS fails or something. So I deployed the loggers and also retrieved the loggers using a canoe, an Avid Canoe Navigator, and a very strong field assistant. In some cases, you'll look underwater, you'll use the snorkel mask, you'll be able to identify the paver pretty easily. It should stand out against the river gravels. If you're not worried about theft or recreationalists moving some device that they find in the river, you could paint the paver so that it really stands out. And then once you do relocate your paver and relocate your logger, you want to have some wire cutters so that you can detach that logger from the paver so that you don't have to carry both in the canoe. Say set your paver on the side of the river temporarily. And then also be sure to just label them immediately as you remove them, because if you're interested in looking at the difference in temperature between, say, the head of the riffle and the tail of the riffle, labeling them as soon as possible is quite important. And then lastly, if you have one of the HOBO portable waterproof data shuttles, you could just download your data immediately from inside the canoe or from the side of the river. So the second field experiment I completed last fall involves the installation of artificial salmon redds in the riverbed. And this was a partnered study that I worked on with the U.S. Bureau of Reclamation and also the California Department of Fish and Game. So some of this work was done in tandem with them. The artificial red study in the San Joaquin River addresses intragravel continuous dissolved oxygen, temperature monitoring, periphyte and biomass, salmon egg survival, and how those parameters compared spatially and under different conditions of flow. So shown in the map in the upper right, 3 sites were selected at increasing distance downstream of Friant Dam, and the sites were selected in the riverbed at the Riffle pool areas that were believed to be appropriate for Chinook salmon spawning. Each location within a riffle was excavated by hand so that we could install the equipment into the subsurface, so between the gravels. And how we did this is we used a 19-liter bottomless bucket to dig the artificial reds. So if you just take a big paint bucket from Home Depot or something and you cut out the bottom, you place the bucket into the stream, wiggle it down, kind of shimmy it down. You could even stand on it if you have really large gravels, and then periodically remove substrate material out and place it into a separate container. So you're excavating just the material that is the diameter of that bottomless bucket. So you're excavating your material, shimmy the bucket down, put the extra material into the bucket, and then once we got to a depth of 46 centimeters, we placed the HOBO Pro V2 loggers plus the dissolved oxygen sensors plus egg plates into the hole and then returned all of the salvaged material back on top of it. So in this case, we didn't use solar shields because the loggers were going to be in the gravel for the entire period of the experiment, and we wanted to see what was the correlation between salmon egg survival in the egg plates at that depth and temperature, and also dissolved oxygen. So continuous hypereic water temperatures were measured in each of those artificial reds. There were a total of 18 sites, so 18 places where we installed those artificial reds using the buckets. And what we were measuring with those loggers in that case was intragravel pore water temperatures rather than temperatures in the water column. So we were able to identify flows and locations with temperatures that would actually be suitable for Chinook salmon spawning if this river were to be restored and salmon were to be reintroduced. There's also a reference at the bottom of this that shows some of the other work that we did as part of that study. The third field investigation that I mentioned, I completed last fall also, and it uses 2 kilometers of fiber optic cable. Fiber optic distributed temperature sensing is a somewhat new technology in hydrology that's used to measure high resolution near bed temperatures, and in this case I measured temperature every 2 meters along the length of the cable at a time interval of every 5 minutes. So today I won't be focusing on the cable itself, but an important part of this experiment involved calibrating the data collected from the length of the cable using HOBO data loggers. So shown here is a picture of the fiber optic cable that was installed along the bed of the river over a length of 2 kilometers. So since the cable is long and it's measuring a temperature signal every 2 meters, our field design included reference sections along the length of the cable, and those reference sections consisted of an independently logged water bath and an independently logged calibration coil, and the calibration coil was secured to the riverbed in the stream. And they were assembled, that coil was assembled as we were installing the cable along the riverbed. So the HOBO loggers are important because they're used to provide the independent measurements that are later used in post-processing to correct any data provided along the length of the cable. So the cable, it incurs attenuation losses in a signal that detects light attenuation through the length of the cable. We use that as a signal of temperature, and using a known temperature from the HOBO data loggers allows us to calibrate in the lab afterwards. So this is just a map that's kind of showing our field design and our layout at the meander bend scale. So our field design, the cable was installed over 2 kilometers, and the red dots are just GPS points taken as we laid the cable. So that's pretty much the line of where the cable was located. The white boxes are showing where the calibration baths, so the calibration baths were in those coolers that I showed in the previous slide. The calibration baths are what contain the HOBO loggers and are constantly measuring that independent temperature. And then there's also the identification of the location of the artificial reds. So those little orange boxes in the lower left-hand corner are one of the 3 sites. So this is actually Site C, where the artificial reds were installed at 6 different bucket locations. So the study area shown here focuses on 3 different meander bends. You can sort of see where those happen. And the high-resolution measurements from the cable, once calibrated with HOBO loggers, supports the analysis of process inference, which is what my research is mostly interested. So specifically, we're interested in the drivers and controls of groundwater exchange, if any, that occurs through the gravel riffles at a number of different flows across these 3 different meander bends. So now I'm just going to take a few minutes. We don't have a whole lot of time left because I'll leave time for questions, but we'll leave a few minutes to look at what some of the data look like. So once you retrieve your temperature loggers from the river or from the lake or coastal situation that you're studying, how we began to analyze the data. So this first example of data that I'm showing is from the Riffle pool study, that first study that's deploying sensors on the pavers right into the bed of the river to collect temperature at the near bed. So I wanted to collect temperature at the sediment-water interface. And the plot shows near bed temperature at several different Riffle pool locations. Those loggers were measuring temperature every 15 minutes, but just for simplicity, this plot is showing data aggregated to mean daily temperature. And we started the deployment in February of last year, and then we ended the deployment in the end of September of last year. And then for the very last month of the deployment below Friant Dam, we also installed loggers in the headwaters of the San Joaquin River for that month that we consider to be the hottest month, the month of August, just to have a reference headwater site to compare, how do these riffle pools differ from the headwater riffle pools? So in general, as you can see from the plot, temperatures began to increase in the summer months, even though flows remained quite high in the summer of 2011, and this was due to a very late spring snowmelt, and because of that, the flow releases from the dam continued to stay quite high through the summer. Temperatures at the riffles in the gravel-bedded reach were cooler than those in the sand-bedded reach. Temperatures in the headwaters were much cooler than all of the riffle pool temperatures in the lowland reach below the dam, and those headwater riffles are shown in the purple lines. Temperatures at the heads of riffles were not always cooler or warmer than temperatures at the tails of riffles or bottoms of deep pools. In some cases, the pools remained warmer than the heads of the riffles, but we're still in the process of analyzing the data, so I'll hold off on making any final conclusions just yet. So what this plot is showing is, these are 2 plots showing data from the subsurface loggers that were placed in the gravel as part of the artificial red study. So those that were placed at a depth of 46 centimeters into the gravel. The top and the bottom plot compare all sites, so all 18 of those artificial red sites across 2 different flows. So the top plot is showing September 29th to September 30th. During this time, flows were held relatively constant at 9 cubic meters per second, and the temporal dynamics of subsurface temperatures strongly followed surface temperature patterns, and daily maximums occurred between about 4 and 5 p.m. at all three of the sites, so sites A, B, and C. The subsurface temperatures generally did not lag behind diurnal surface temperature patterns by more than about 30 minutes. Due to increasing air temperatures during this period, the end of September, the thermal maxima on the 29th, for example, exhibits a gradual recessional limb rather than a more distinct decrease to nighttime thermal minima, which is what we would expect to see by measuring subsurface temperature. So this suggests that both surface and subsurface temperatures are closely in phase and driven largely by atmospheric conditions during this period. The bottom plot, though, is showing flows at 20 cms. So this is a high flow pulse that occurred in October. The temporal dynamics of subsurface temperatures somewhat followed surface temperature patterns. Daily maximums occurred between 3 and 4 p.m. or between 4 and 5 p.m. as you got farther downstream. The subsurface temperatures were typically in phase with respect to timing, with a few exceptions. So of those 18 sites, there were a few distinct sites that exhibited a 4 to 5 hour lag to reaching their peak thermal maxima each day compared to the surface water temperatures. So subsurface temperatures were showing a lag and also a little bit of a buffering, which is what we expected to see at some of them, although we didn't see it at all of them. So a second set of plots that comes out of the report that I cited earlier is also from the subsurface loggers, and these just show individual locations. So for example, if you see site B4, during this October high flow pulse, the flow is shown in the green line. We did see a very extreme difference in the subsurface temperature, which may suggest some influence of groundwater coinciding with the high flow release from the dam. So we're still looking into this a little bit more and looking at some of the data coming from the DTS as well. And the subsurface, the range of temperatures at all three of the sites was greater in the end of September than in the end of October for both the subsurface and surface water. And the reason for the diminished variability of temperatures towards the end of the experiment we attribute to two possible reasons. So one could be that the mobilization and deposition of fine sediment during the high flow resulted in diminished permeability between the gravels, which is correlated to lower conductivity, longer residence time of intragravel pore water, and buffered connectivity to surface water. The temporal dynamics of surface temperatures strongly followed air temperature, and maximums occurring in September and minimums occurring in November. So towards the end of the observation period, differences in surface water temperatures and subsurface temperatures became less distinct, and this indicated that the decreasing day length and lower maximum air temperatures over the course of the experiment did play a big role. And then this is again the same data, but just really simplified to just compare the three sites, sites A, B, and C. So just to wrap up, I'll just mention the very last example of data, which is that from the fiber optic distributed temperature sensing data. And this data was calibrated using the HOBO temperature loggers, as I mentioned before. So what's shown here is a temperature trace taken from the very beginning of that experiment. So right after the cable was installed in the bed of the river, so right around October 9th. The temperature traces are symmetrical, so what's that's showing, if you look on the left side of the graph and the right side of the graph, the cable is spliced. So there are two fibers within a single cable. They're spliced at the end, and that allows us to have two temperature observations at every point along the cable. So that spike in temperature that you see in the very center of the graph shows the location of the splice, which in reality is pulled up and out of the water and it's sitting on the bank. So the reason that there's a spike in temperature is because it's measuring air temperature. And then as you look farther to the right on that graph, we're not going farther downstream. We're now showing data of the fiber, the second fiber, and the data going back up parallel to that first fiber inside the cable. So what we see basically is that all of these traces of temperature at the beginning of this experiment showed relatively uniform temperature along the bed of about 15 degrees Celsius during the period of initial setup. And what we were interested in was taking all of the data over a month and looking at how that changed over different flows and at different places along the bed, and then comparing that to our previous Riffle pool study. So I think the take-home message from this slide is really that the instrument calibrates the data along the length of the cable itself, but recalibrating that data becomes very important, and using the independently logged temperature from those baths is how we do that. So just to wrap up, I think just to mention, there's been a lot of different forms of support that have allowed me to conduct this research and do a pretty lengthy field experiment. And also thanks to the U.S. Bureau of Reclamation, Mark Nelson and Greg Reed, Eric Guzman and Matt Bigelow from the California Department of Fish and Game. They were my collaborators on the artificial red study. So I'm going to read through some questions right now, and also invite Paul or Cynthia to come back on if you want to ask any additional questions that you might have received. So,
all right, I'm back, but I'll let you. Most of the questions I see are related to the application, so I'll let you you go first.
So I think some of the questions were, let's see here. So some of the questions, there's a couple of questions about how do you decide what your time interval for temperature would be, why, you know, a certain amount of time for the DTS, for example, which was 5-minute intervals, and why 15 minutes for the other loggers. So to answer that question, the Riffle pool study was intended to be a long-term deployment over very high flows and very low flows. So the memory on the HOBO data loggers is limited if you're going to leave it out there for a long time. So the 15-minute interval was selected so that I could leave those loggers and not move them for as long as possible, because I wouldn't even be able to access them, for example, when flow releases from the dam were 7,000 CFS. So that's the reason why the loggers were operated at 15-minute intervals for the Riffle pool study. For the DTS study, which was the third study, I was only leaving the equipment in the river for a period of 1 month, and it was only going to be subject to flows of 350 CFS up to 700 CFS, and then down to about 100 CFS. So I wasn't as concerned with mobilization of the loggers, and I wasn't in need of a really long data set, so I didn't have to worry about memory. So it was fine to set those loggers at the same interval that the DTS was collecting data. Paul, there's some questions about the solar shield. Do you want to say a thing or two about those? I know we got our solar shields from HOBO, but maybe you can describe those.
There's a couple of options. So first off, you have to. The first question is whether you need a solar shield or not, and that's very much related to the depth that the data loggers will be at. in a pretty high flow rate system like these rivers, I would say if you're shallower than 2 feet, you probably need to do some sort of solar shield. I don't know if that matches with your experience, Aaron, but if it's deeper than 2 feet, usually the light is attenuated enough that it's not going to cause the logger to heat up too much. What you're trying to do is with the solar shield is you want to make sure you're measuring the true water temperature and not measuring the data logger itself being heated up by the sun. So yeah, look at your depth, and if you're shallow, then you do need to worry about it. And we offer for our loggers basically we call it a boot. It's a white boot that reflects most of the solar radiation, so it minimizes the heating effect on the logger. Another choice is to put some sort of shield immediately above the logger, but then that gets tricky because it might get caught by debris flowing by, or so usually your best approach is to use a boot on the logger to minimize the solar heating. So, you have anything to add to that, Aaron?
No, I think that's pretty straightforward. I would definitely recommend using a solar shield. I mean, even in a large river, when we're interested in looking at riffles and pools, even when flows are high, the heads of the riffles are fairly shallow, and the groundwater exchange is topographically driven, so just over the length of the head of the riffle to the tail of the pool, there's a pretty big difference in depth. Especially at low flows, that difference in depth is greater. So you will have some loggers that are in pretty shallow depths if you're studying, if your research or your work is focused in these kind of meander bend types of areas. So I would recommend coming up with some sort of strategy. It may not need to be the boot per se, but some sort of strategy to account for the solar heating. And there have been a few papers that did estimate this, the solar heating that happens for certain types of equipment. I'm not sure that any have been done for the loggers themselves, but the loggers are black, and
yeah, there was a question actually on the color of the loggers. Why didn't we just make them white? And the reason for that is in some cases you need to camouflage the logger as best as possible, and the black was chosen for its camouflage ability if you're on a black bottom. But then there's always a trade-off, so that's why we offer the option of the white boot.
Yeah. The boots also, if you're going to leave your loggers out for a long time, somebody had a question that we're reading about this. If you're going to deploy loggers for a long time, the boots are actually fairly protective also. So if you're worried about large woody debris getting swept down the stream during the course of your experiment, those little boots are actually pretty sturdy and can just help to make sure that they don't cause any sort of turbulence or woody debris doesn't smash your logger. And then the way that I installed the Riffle pool loggers is just to take the paver, attach the boot and the logger to the paver, but then I actually placed the logger on the bottom of the paver, so the only thing that was up in the water column was the paver, and the logger was kind of nestled down into the gravel. So that was also good for protecting it from any sort of snag or something else that could be carried downstream.
Yeah. Actually, switching to a different subject, I've seen several questions on the pit tags. Aaron, could you describe what those are and how those were used, just to clarify for those that aren't familiar with using those?
Yeah, so the pit tags, I'm not going to remember right at the moment what that acronym, those exact words, but the pit tags are used, in a lot of different, if you wanted to trace maybe like the movement of gravel or something, The pit tags are just, they can be detected. So you can buy those little tags, but you need an antenna that detects them. So it's like a little mini relocation sensor that you could use. And there are problems in relying on that to retrieve your sensors, and in our case, more often than not, we relied on GPS data. So I wouldn't run out and purchase a pit tag antenna unless your organization already has one. Then it's great to have just that as an extra backup. The pit tag antennas that you use when you go out to retrieve your sensors, it's kind of like almost like a little metal detector or something. The one that I used, you couldn't put it underwater, so you had to hold it right above the surface of the water and just kind of move around slowly over the area where you believe that you left your logger. So the range of those antennas and how accurate or precise they are varies, and I don't know that much about kind of the differences in pit antennas that are available to purchase, but you could look into it and see if there are ones that are either waterproof or ones that are very, very precise. So in our case, you would have to be really pretty close to where your logger actually was for the pit tag antenna device to start beeping and say, you're right on top of your logger, here it is. So we used that more as a backup than anything, and relied on the GPS data to relocate our sensors, and then did a great deal of snorkeling and just looked around. And in some places where we weren't so worried about camouflaging, we put a little bit of paint on the pavers or something to kind of help them to stand out.
One of our attendees actually sent in the meaning or the translation for the pit tag. It stands for Passive Integrated Transponder. So thank you for that.
Great. That's what it stands for. Thank you.
This is great. Lots of good questions.
Let's see here.
There's a couple questions related to quantifying the flow rates based on the data. I don't know, maybe you can find one or two of those and try to address that. That's probably a big topic.
Yeah, so there are some questions about detecting influences from groundwater intrusion from the mine pits on the side of the river, and are those temperature loggers sensitive enough to detect those differences. So again, the thing that you should keep in mind when you're deploying your loggers is that if you're putting them, even if you're placing your loggers right at the bed, that's still measuring turbulent flow in the water column. It's not measuring laminar flow between groundwater, between pores in the interstitial spaces between the pores. So there is some mixing that occurs even right at the bed between any groundwater that might be coming out of the bed in the form of upwelling and just the turbulent flow from the river. And in a large river, it's going to be hard to detect any sort of difference if you don't also have other data to inform it. So my kind of overarching response to this would be, no, you could not rely only on HOBO temperature logger data to try to detect groundwater just by placing them in the riverbed. You could try to come up with an array of HOBO temperature loggers placed at different depths, which several people have done, so that you have kind of an array with depth into the substrate. That way you can look at changes with distance into the bed and then changes over the length of the bed, as well as changes from the bed to the top of the water column, which would require some sort of rebar or suspension device in the water column. So also, most of the work that has been done also requires other data. So if you use pressure transducers, or you take measurements of vertical hydraulic gradient, or just go out and measure water depth over different flows, you need some additional data in addition to the temperature data. So this was focused a little bit more on what's a good way, or what are some successes that we've had in measuring near bed temperature and subsurface temperature using the HOBO data loggers, but none of the work was done without additional field studies. So someone asked about cross-channel temperature variations. We actually we weren't looking at cross-channel temperature variations in any of the studies. So the artificial red studies were really showing with distance downstream, sites A, B, and C. The Riffle pool study was showing longitudinal differences in temperature over space, so at the head of the riffle, the tail of the riffle, and then farther downstream at the bottom of the pool. And then the DTS fiber optic cable was installed just longitudinally from upstream to downstream and was positioned as closely to the center of the channel as was physically possible to install. Let's see here. Someone has a question about flows in tropical rivers. They're very turbulent. You lose a lot of loggers. Are there ideas about how to anchor the loggers so that they don't get carried away? I think, again, I would avoid tethering them if at all possible. And in this river, we didn't want to cause any disturbance to the bed, so anchoring them was very helpful. If it's possible to use some sort of cinder block or concrete paver that's quite large, and you can get someone to drill a hole right into the center of it, it's most likely not to be broken, and if you can kind of position it pretty securely into the bed or put gravels on top of it, we found that worked well. We were pretty surprised that it sustained flows of 7,000 CFS. That was a very, very high flow. But it meant that, this seemed to be a pretty tried and true method.
I think that's more a question for him. Yeah. There was
yeah.
I was just going to suggest there was a question about what software you used to do some of this analysis.
Sure.
Can you talk about that?
Well, do you want to first describe just the software that's used to download the HOBO data loggers? So when you order your loggers and you're ready to set up your field experiment, you'll be able to offload that data using a device that's also purchased from Onset, who makes the data loggers, and then it will read out your data. And so you do need the appropriate software, which I think you can even download online.
Yeah, we have it available for download, for a fee, of course. It's HOBOware Pro, and yeah, that's used to set up the loggers and offload the data. And it includes, a fair amount of graphing and analysis capabilities, but we find that most of you end up exporting it to the data, other programs, and we've got easy ways to set up the export so that you can get it formatted in the right delimiters, like tab delimiters or whatever, for the program that you're going to be importing the data into.
Mm-hmm. Yeah, the software, I mean, there's a lot of different kinds of software, and I don't recommend one in particular over the other. I think you'll understand your data the best if you use the software that you're most comfortable with. You could use Microsoft Excel. I mean, when you download the data from the loggers, you can open it up in a spreadsheet right away. You could also analyze your data using something like R or MATLAB. There's also a program called JUMP that is more of a statistical software, but again, I don't recommend one in particular. I think it will also depend on what you want to do with your data, or if you just need to plot it to kind of show graphically what are the trends. So. Someone asked about using epoxy to attach the logger to larger rocks. I actually never used epoxy for loggers. I did use epoxy for a different study with piezometers to seal up some holes in a pre-made piezometer that was steel. And if you're putting anything into the substrate and it's a gravelly bed and there's going to be any force in trying to put it there, you'll probably lose your epoxy, or it'll probably, the point of losing your logger will be the epoxy. If you're just going to place the rock in the river, there are some epoxies that people have found to work well, and I think there's actually there is a paper that evaluated maybe 5 or 6 different kinds of epoxies, and if you email me, I can give you the citation for that paper.
Yeah, we actually, I think we have that paper, or maybe a similar one, on our website. Involved, I think it was actually a webinar where one of our users talked about using epoxy to mount the data loggers. So, yeah, we'll include that as part of the follow-up for this. A link to that.
Mm-hmm.
You know what? I'm just looking at the time, and maybe we've got time for one more question, and then we should wrap it up.
Yeah, sure. Let's see. So someone said, you know, for smaller rivers, you could just use bricks. So if you're not worried about someone picking up a brick and pulling it out of the river, you could use bricks because they already have precast holes in them, and it doesn't require drilling. There's one other question about how, you know, what is the impact that the sediment can have on the temperature measurements, and how can we decide whether the sediment is kind of ruining our temperature measurements or making the data set unuseful. Well, if you're interested in measuring stream channel water temperature, then you don't want to use any data that has been inundated with sediment. If you're interested in measuring pore water temperature in the interstitial spaces in the ground or in the subsurface below the riverbed, then you want to know what is the sediment grain size and also how deep is the sediment cover that's you know, that's covering up your temperature logger, that's separating it from the flow in the water column. So I think that any involvement with sediment can be fine if you're documenting how deep it is and what's the, you know, say the D50 grain size or something like that. So I think we're going to need to wrap it up here, but I'll thank everyone for calling in, and thanks to Onset for hosting this webinar. And again, my email address is included here, and I invite anybody to email me with questions or particular field methods that you've tried or wanted to discuss. I'll be working on this research for long foreseeable future, so please feel free to get in touch, and thanks again for joining.
And thank you, Erin, so much for sharing your expertise with us. This has been very informative.
Okay.